Hello, this is Patrick O'Shaughnessy, and this is the 9th module in the series Statistical Methods for Analyzing Data Obtained in the Lab or Field. In this module, we'll focus in on this concept of the sampling distribution and finish with the t-distribution. Here is the module map associated with this 9th module in the series. In this grouping of statistical tests, you can see we started with descriptive statistics and then on to continuous variables, the normal distribution. Now we're furthering our way towards our ultimate goal of understanding what a statistical test is with some of the underpinning statistical hypotheses and theorems that are associated with a statistical test in this module. It is very important, therefore, to review this module before the next one. Okay, so back to the concept of central tendency and variation. We've talked about a mean and a variance and a standard deviation. Ultimately out there is a kind of out there in the field, in the lab, there is an ideal of what those means and standard deviations are of the population. So these are what are called parameters. When you talk about the mu and the sigma, those are important concepts to help describe the distribution of the parent population that is ultimately unknown. The best that anyone can do typically is to take samples from the population, and therefore we have to talk about a sample mean and a sample variance, sample standard deviation. These are what are known as statistics, and that'll become obvious in a quick moment here. So again, they're calculated from a sample that describes some important feature of the sample. Okay, so if you're sampling from a population, you can take one sample and it will contain, say, n observations. You need at least 2, but hopefully you have 10, 20 observations. Now you may take that one sample from the population, or you might take multiple samples from the population. And then recall that you can determine a sample mean easily by summing up your values and dividing by the total number of observations. Okay, so we can do that once for the first sample you take. You can do it again for the next sample you take, etc. That means you can take multiple samples and obtain multiple sample means, these y-bars. If that's the case, then it would be highly unlikely that any one mean is exactly the same as another mean. Therefore, they will have a distribution as well. And this distribution is given the name of the sampling distribution. So that ing after sample is important. It is the distribution of the means, not the distribution of all of your observations. And this again is why the means are called a statistic, because they have a distribution. The same thing is true for a standard deviation, which could also be calculated for all of these samples, right? And so you could actually end up with a standard deviation of the standard deviations. But let's move forward here. And so we're now going to talk about the Central Limit Theorem. This is an extremely important concept that guides our understanding and our abilities to make inferences between populations. That's ultimately the goal of statistics. So first of all, we're going to assume that you have n observations from a random sample from the population. And then the population has a finite mean and standard and variance. It's not constantly changing. There is a value there within the population that is fixed. It's like the ultimate mean of all student heights at the University of Iowa. And then ultimately you have a sample with a number of observations and that is quote unquote sufficiently large to be able to understand and have enough values to have a distribution of them that spans the range of values within the population for the most part. I have to say for the most part because there's those that are infinitely small, typically infinitely large as possibilities. Okay, so then the central limit theorem states that the sampling distribution of the estimated mean can be approximated by a normal distribution. Oh, okay, so that's good. So this distribution of the means of your samples will be approximated by a normal distribution almost regardless of what the distribution of the observations is. This is interesting. Okay, so that means that the mean of all of your means, the means of the y-bars, will approximate the mean of the population almost exactly. And the standard deviation of all these y-bars can be expressed by this function here. It is related to the standard deviation of one of your samples divided by the sample size. Now that one is interesting and almost shocking, and we'll get into that concept here. So this standard deviation divided by the square root of n is called the standard error. So this is the first time we have formally described the standard error as versus the standard deviation. Obviously, if you're dividing by the square root of n, the standard error is necessarily smaller than the standard deviation. So, and again, n is the number of observations for just one sample, and sigma is the standard deviation of n observations from one sample. So ultimately, that is an S in a sense. It is a sample S standard deviation. Just using the kind of the Greek notation here. So this means that you can have a good estimate of the standard deviation of the means really just based on one sample. You don't need to take multiple samples, collect a bunch of standard deviations from those samples, and then come up with a standard deviation of those standard deviations, as I talked about. The central limit theorem implies that the standard error computed from one sample is sufficient to accurately predict this standard error or the standard deviation of all of your means. Okay, let's try to visualize that now. Okay, now let's take a look at an example of the use of the central limit theorem to try to tease out all these means that we're talking about and standard deviations and standard errors. Okay, so first I developed an Excel spreadsheet using one of the functions in the data analysis tool pack that allows you to produce random values. In this case, given a desired population mean of 10 and a standard deviation of 1. Populated 100 columns with 100 observations. Each one of them a random set, hopefully, with a population mean of somewhere around 10, standard deviation around 1. Then went ahead and produced a histogram of all 10,000 observations, and you can see the result here. This is, as expected, extremely well-defined normal distribution, just as you'd see a typical hump-shaped with curves. Then it ranges from around 6 to 14, which is also expected. You can see the actual mean of all 10,000 was around 10.009, and the standard deviation was 0.993, so very close to the expected values that are generated by the random number generator. So this is the distribution of the observations as we've been talking about so far in these modules. How are your observations within your population distributed? Okay, now we have to start talking about a different type of distribution, the sampling distribution. So to get at the sampling distribution, technically, or one way, is we have those 100 samples, 100 columns, to compute a mean for each one. Right now I have 100 means, and again, they're not exactly the same, so they have a distribution, and that's what you see here. But we wouldn't expect that the distribution of the means would be as broad as the mean of the observations, right? The means will be packed very closely to the center of the distribution of the observations because they're the means. So again, here it's not quite as well distributed, but it is somewhat mound-shaped, and that's what the central limit theorem tells us, that the distribution of the means will be approximately normally distributed, and that's what we see here. But the range is only from 9.75 to 10.25, much narrower. And again, that would be expected. So this is not the distribution of the observations. This is the sampling distribution of the means. You're going, why is this so important? Well, all statistical techniques, like the t-test that we'll come across, deals with this distribution, not the distribution of the observations. With a t-test, we're interested, is the mean of this one group statistically different from the mean of another group? We don't care about all the observations being different, just the mean. So we use the distribution of the means to get at that question. So as given earlier, the actual mu of all the y-bars, 10.009. Of course, it's very close to the 10 that we expected. And the standard deviation of all those means, which we now call the standard error, right? Technically, from the ideal population, had sigma was 1, divide by the square root of 10, you get 0.1. Well, that's really close to the overall mean of those sampling distribution we just saw. It was around 0.099, something like that. But here, just taking one of the 100 samples, throwing in its sigma, which was around 1.015, as we also would expect, divided by square root of 10, you get 0.1. So again, the standard error approximated from any one sample comes very close to obtaining the actual standard error of the entire population. And that's what, again, what the central limit theorem states. So we've more or less just proven that to ourselves. So it's a very good estimate of the standard deviation of all the sample means. So now we have a overall mean and kind of an overall standard deviation of the means, just the means themselves. Now looking at the distribution of them, again, the observation distribution will be broader than the distribution of the means. They are going to be packed around the center because that's where all the means, if you calculate them from a variety of samples, some of the samples are shifted maybe a little to the left of the actual mean, some a little to the right, but most of them are going to be really close to having values that are spread out across the observation distribution. So then a majority of the means will be in the center. So this is, in this case, shows where sigma was 1 for the observations and a sigma of 0.1 for the sampling distribution. So again, when we do a t-test, we're using the red distribution, not the blue. Is the mean of the population. We don't quite know, but we know it's ranging somewhere around here to here. That's what we now know. Is that different from another population, maybe with a sampling distribution sitting over here? Again, we don't know the exact number. If we knew the exact number, we wouldn't have to apply statistical techniques. So we're always kind of guessing. We know the true mean is somewhere in here, and we're comparing that to some other set of values. So when testing two samples to determine whether they are different or not, the sampling distribution is used, not the distribution of observations. So I'm trying to emphasize that yet again here. Okay, let's now talk about the t-distribution. We remember what z is from previous module. It is a standardized set of values that have a mean of 0 and a standard deviation of 1. Now we can do the same thing for the sampling distribution, except instead of an observation, we have y bar here, the mean of our sample, and the standard deviation of our sample divided by the square root of n. So we're using, instead of dividing through by the standard deviation, we are now dividing through by the standard error, as shown here. Again, we would have to substitute in S for sigma when it is from a sample itself. We use sigma if we have a bunch of historical records and we know we've done this over and over and over again, have a really good idea of what the standard deviation truly is. And that's ultimately what you need to do when applying this formula here to create this z value. Again, if we don't know sigma, we need to estimate it. So we need to replace sigma with its estimate, which is the calculation of the standard deviation, which we went over in module 1. And so we just substitute that in, as shown here. And we end up with another ratio of this difference divided by a standard error. But the wise ones of old, as you could say, notice that this distribution didn't follow a normal distribution as this one does exactly every time. And so this caused them to rename this set of values they can get out of this ratio here as a different distribution called the t distribution. There's reasons for t that you can look up on Google. So they realized again that t distribution is not normally distributed. It has what's called a t distribution because of this issue of having this estimate of sigma s as an additional source of variability. So they also noticed that the t distribution is highly dependent on the sample size n. So the shape of the t distribution changes with the number of what they call the degrees of freedom, which is a function of the sample size of n. Whereas the shape of the z distribution, even this sampling distribution up here with sigma, is normal and is independent of n. Okay, so what does all that mean? And what do the degrees of freedom mean now that that's been introduced? Well, it's somewhat complicated. Talk about what this concept is, which goes beyond the intent of these modules. We just have to understand that when utilizing a t distribution, we are dealing with this concept of the number of what are called independent information is present to estimate the standard error. And again, it's been developed that the amount of independent information you have, called the degrees of freedom, is related to the number of observations and then the number of parameters that are estimated. For a t distribution, we just talked about sigma being the parameter that is being estimated. So p is 1 for a t distribution, and therefore the degrees of freedom will be n minus 1. So it's as simple as that for the t distribution. So here's off of a Wikipedia page, credit them, thank you very much, that shows this degrees of freedom, this kind of Greek letter, eta, I believe, being 1 is coming from only a sample size of 2, right? So 2 minus 1 equals 1. So you can see that the distribution for when the degrees of freedom are 1 is lower than the others, and it spreads out much further in terms of the tails of this. The tails are thicker, as it says, with low v, the low degrees of freedom. And this ultimately causes greater uncertainty in our estimates or abilities to distinguish populations. You can see as the degrees of freedom increase, you go, so n of 20, for example, will give you a degrees of freedom of 19. You go up to n of 100, degrees of freedom are 99. You see the difference between the observations and the degrees of freedom gets less and less, in a sense, relative to the number of observations. And you ultimately get back to the normal z distribution, which is here in black. So this is a perfect normal distribution in black. You can see how those associated with the t distribution vary from their maximum to their minimum here. So that has to be taken into account when determining t values that we'll talk about later. A t table that you would find in the back of a stats textbook often looks like this. It doesn't deal with the probability under the entire curve. It only deals with the probability in the tail areas. So as we see over here, and again, that will become more apparent in the next module. So if your tail area is 0.05, for example, that means 5% of the distribution. What we'd like to know is, what is this value right here that delineates between the rest of the distribution and that tail area of 5%. To know that, we would come down and we would go to the degrees of freedom. So for a sample size of 9, I would have to be on the row for 8, which is n minus 1. Come across here and see 1.859. So that will be the t value associated with a 5% probability in the tail. And again, we'll see this more when we get into utilization of the t-test.